Welcome to the new lecture, and let's pick up from where we left last in the last class. So in the last class, we talked about the laboratory consolidation test, and we discussed that in the laboratory, whenever we are talking about consolidation, basically there are two things that we need to find out, or we are interested to find in finding out. One is the magnitude of consolidation settlement, which is actually determined by a parameter called the compression index, and the rate of consolidation, which is determined by means of coefficient of consolidation. And if we know these two things by using the magnitude and the rate of consolidation, we can actually determine the time required for consolidation as well. And in doing so, in the last, we also discussed that whenever we perform the consolidation test, so while performing the consolidation test, there are three main observations that we take. We take the observation of the load or the pressure. We take the observation of the dial gauge reading, and third is the time. And by using these three uh, observations, we generally plot two types of graphs. One is the time versus deformation curve, and second is the pressure versus deformation curve. The time versus deformation curve is what we use for the determination of coefficient of consolidation, something that we discussed in detail last week. And the pressure versus deformation curve can be used for the determination of compression index. And we also briefly touched upon that it does not only uh, help us evaluate the compression index, but it also help us determine some other useful parameters listed herein. So our today's discussion is the pressure versus deformation curve, and let's see how we can plot the pressure versus deformation curve, what are the different components, and how we can determine all these things. So let's focus more on the pressure versus deformation curve. So this, when we talk about the pressure versus deformation curve, now this pressure is quite simple for us, that we apply a load, and this load gets converted into pressure by means of this green colored plate. So this point load, we divide this load with the area of the plate to get pressure. So that's quite simple. But how do we measure deformation? In a consolidation test, this deformation is generally plotted in terms of void ratio. So the dial gauge readings that we are observing, which are the representative of the soil deformation, we have to convert those dial gauge readings into corresponding void ratio. And I believe you can have a very good idea about this, that the change in void ratio can actually represent the deformation in the soil. So we use void ratio to represent deformations in the soil. Okay, so then we plot two different kinds of graphs. Typically, one is the void ratio versus pressure plot, where, or we call it as the E versus P plot. And the other important graph that we make is the void ratio versus log of pressure graph, E versus log of P plot, we call it. So let's look at them in more detail one by one. So what does E versus P plot look like, and what are the benefits, how to plot it? So let's think for a moment that if I want to plot the relationship between the void ratio and the applied pressure, what do you think? When I'm increasing the pressure, by increasing the pressure in a consolidation test, what should happen to the void ratio? You might have guessed it, that when we increase the applied pressure, by increasing the applied pressure, the soil gets compressed. And when the soil gets compressed because of compression, its void ratio should decrease. So if the void ratio should decrease, so by increasing the pressure, which is plotted on the x-axis, you see when I'm increasing the pressure, the void ratio is decreasing. So this is the typical trend that we see. This is the typical shape of the graph that we see when we talk about E versus P graph. Now on this graph, what we can do is, if we determine the slope of this graph at any particular location, if we determine the slope of this graph at any particular location, the slope of this graph is represented by a parameter A subscript V, and this AV is known as coefficient of compressibility of soil. So if you remember in the previous slide, we saw that by using the pressure versus deformation curve, we can determine four different parameters: the compression index, the recompression index, coefficient of compressibility, and coefficient of volume change. So this is the first one. So if we want to determine the coefficient of compressibility, we can determine coefficient of compressibility simply by taking the slope of E versus P graph. However, if you look closely, there is a little problem with this slope. What is the problem? The problem is that this graph is never a straight line. This graph is a curve. Now, if this graph is a curve, it means the slope of this graph is changing at every position. So what it means is that if I determine the slope at these 2 points, it will give me a different result. And if I determine the slope by taking any 2 points here, it will give me a different result. And similarly, I'll get different result if I determine the slope of this line at any different location. It means that this AV, which is the coefficient of compressibility, it becomes a function of the applied pressure. So at a different range of pressure, there will be different value of AV. Now, this makes our calculations of consolidation settlement a bit more complicated. What we actually want is we want a more consistent solution in which the slope of this line should not change. And you know, when does the slope of this line does not change? Only if it is a straight line. So what we can do is we can change, instead of plotting E versus P, we can plot a graph between E versus log of P. Now, if I plot a graph between E on the void ratio on the y-axis and pressure, log of pressure on the x-axis, we get a straight line. And if we take a slope of this straight line, now the slope of this straight line will always be constant irrespective of the applied pressure. Now this is a huge benefit of this graph. And the slope of this line, the slope of the line with the straight line in an E log P graph is something that we call as compression index, C subscript C. So you see, what is compression index? Compression index, which we have already discussed, is something that we use to determine the magnitude of consolidation. So this compression index is simply the slope of the line in an E log P graph. So this delta E comes from the y, from the ordinate, and this denominator comes from this denominator here. Okay, so these are the two main graphs which can be plotted. However, there is a third graph which can be plotted here, and that third graph is we sometimes need to plot the graph between strain and pressure. So instead of void ratio, the deformations we can plot in terms of strain. If we plot the deformations in terms of strain, we again get a graph which is similar in its shape to the E versus P graph. So it is a curved line here, and the slope of this graph is something we call as MV, and MV is which is the coefficient of volume change. So this is again something that we have discussed in our previous classes. You have seen that we have also discussed some relationships between coefficient of volume change and coefficient of permeability. So the coefficient of volume change is simply the ratio between strain produced on the application of unit pressure. And further, there is an interrelationship between this AV and MV. And if you know the value of AV and the void ratio, you can easily determine MV by using this simple expression. So this expression is also very useful many a times. So as we have discussed so far, that this graph, which is the E log P graph, is the most important one. It is the graph which is most commonly used by us in our calculations. So, and this is the same reason why this CC, which is the compression index, is a parameter which we most commonly use for the determination of magnitude of settlement. So what we'll do is let's explore this graph a little bit more in detail. So let's explore this graph a little bit more in detail, and let's see some of its components. So this graph, the E log P graph has void ratio on the y-axis and log of P on the x-axis. So we have seen that the trend is a straight line typically, and the slope of this line is what we call as compression index. Now, this line is generally called as the virgin compression line. Why so? Because this line represents the soil behavior in which the soil has for in its entire loading history for the first time being compressed. So this is why it is called the virgin compression line. Then you might remember from our discussion on when we talked about the performance of the consolidation test that once we apply all the loading increments, afterwards we apply unloading as well on the soil sample. It means, so once we increase the load, the void ratio reduces. We increase the pressure, the void ratio reduces further. We increase the pressure and the void ratio keeps on reducing till this point. Now, once we have applied the maximum pressure, what we do is then we start reducing the pressure. And when we reduce the pressure, what should happen? When we reduce the pressure, the soil which was initially being compressed, when we reduce the pressure, the soil should start swelling back again. Now, once the soil should start swelling back again, it means initially the void ratio was being reduced because of compression. Now, when the soil is expanding, so the void ratio should increase. Now, how the void ratio increases? The void ratio increases like this. So it means when we reduce the applied load, when we unload, the void ratio reduces a little bit. Void ratio reduces a bit further, and go on till we remove all the applied load. Now, important for you to remember is that the soil does expand, but while expanding, the soil does not expand back to its original position. If it was the case that when you unload, the soil expand back to the original case, in that case, this green line would have been on overlying this say, initial line. But this is not the case. This is why this green line lies somewhere over here. The slope, this line is known as the rebound curve, and the slope of this line is called as the recompression index or the swelling index. Now, this is the second definition that you should know, that we already discussed what compression index is. The slope of the unloading curve or the rebound curve is known as the recompression index. So why it is called the recompression index? Because this line does not appear over here only. In fact, although I have shown you this straight line like this, meaning when you initially applied the load, the soil starts getting compressed, but in actual, the soil behavior is a little different, and the actual behavior has an initial line over here as well. It means when you initially apply the load, the, the void ratio change is a little less and the slope of the line is rather gentle. But after a certain point, the slope starts increasing very rapidly. Now, this initial part is something which is called as the recompression curve. Now, this recompression curve has the same slope as the rebound curve. So the slope of this line is also going to be equal to the recompression index. So these are the main components of the E versus log P graph. And from this slide, I hope you would have got an idea about not only the compression index, but also what the recompression index is. So one question that should come to your mind is, why is this curve called a recompression? Isn't it the first time we are putting load and compressing this curve? So why is it called a recompression? The reason why this is called recompression is because, let me try to explain this to you by means of overlaying something here. Now, what happens is, let's assume that you had this first loading curve and then you unloaded the, the soil sample. Now, once you have unloaded, let's suppose you do not finish your test here, but in fact, you again reloading the sample. Now, if you again start reloading the sample, it means the soil will follow this path. The soil will be recompressed here. So you see this line which I'm drawing here, this will be the recompression curve. So this is why, because on recompression, the soil will follow the exact same path as the rebound curve. This is why it is called as the recompression curve. And if beyond this point you further start loading the soil will not follow the straight line. Rather, from this point, soil will start following this path and it will start going over here. So if you are loading, the soil will be following this path. So this is the reason why this curve is known as the recompression. Why this curve is known as the recompression curve, because this recompression curve can be part of this one somewhere. So probably, so in fact, it is this recompression curve is the same curve as we have drawn here. So you can see what I can have is, I can have this recompression curve, then I can have the virgin compression curve, then I can unload from here and I will follow the same path. So this unloading one, if let me just draw it here for you for your convenience. So if I unload the soil from here, from this point, it will follow this path. So this will be the unloading curve. And from this unloading curve, if I start reloading the soil again, so my reloading curve from here would again follow the same path and it will keep going in this direction. So this is why this so this is the reason. Now you can see this central part here. Now in this central part, we call this one as the recompression curve. This is the virgin compression curve, and this is the rebound curve. So I hope you get an idea from here. So just look at the central part here. So this central part, in this central part, this would be the recompression curve. This would be the virgin compression curve, and this would be the unloading curve or the rebound curve. And as explained initially, this rebound curve would have the same slope as this recompression curve. This is why it is called CR. So this is actually showing the behavior of the soil sample when we are loading it. Now, the important thing to note here is, what do you think? Why, when you are loading the sample back, when you are loading the sample, it follows this path, and at this point, instead of going straight here, it changes its direction. Why the slope changes? Now the reason is that this point is the one. If you notice, this is the point at up till which the maximum load has been applied on the soil in the past. What I mean is, let me move to the next slide and try and explain this thing to you. Now, look, on this graph, what has happened is that this point actually represents a special point, which is called as the pre-consolidation pressure. What do we mean by the pre-consolidation pressure? Pre-consolidation pressure means the maximum effective stress experienced by the soil in its entire past history. So what it means is that this was the pressure which was applied on the soil somewhere in the past. Somewhere in its history, this pressure was applied. This is why the slope of the line is gentle here. And this is the part of the graph that this pressure is being faced by the soil for the first time. This is why it's this part of the graph is much steeper. So, so this is why this point of curvature in this graph is known as pre-consolidation pressure. And to explain it a little further, let me just try to draw the same graph here. So this is the pre-consolidation pressure, but if I draw the same graph that I had drawn on the previous slide, you see I'm increasing the load. This is the recompression when I reach this point. When I reach this point, so from this point, this much pressure was applied on the soil sometimes previously in the past. But when I increase the pressure beyond this point, when I am increasing the pressure beyond this point, this extra pressure has never been faced by the soil ever in its history. This is why it will follow the path of the virgin compression line. Now, what is the virgin compression line? Virgin compression line is this one, which is this which has a slope of CC. So if I increase the load beyond this point, it will follow the path of virgin compression line like this. So in this case, there will be, for this second loading cycle, I can say the pre-consolidation pressure would be this one. So this would be the pre-consolidation pressure, sigma P dash, for the second loading cycle. So I hope with these limited tools, I would have still made it a little clear. The rest we can discuss in our online discussion session. But let's move forward, and I'll try to explain this concept a little further to you. Now, what it means is that there is a significant effect of stress history on the soil. What, what do we mean? So you see the stress history, whether the load that we want to apply on the soil, was this much load applied ever in the past on the soil? Was it the case or not? This changes the behavior. This changes the deformation behavior of the soil. What I mean to say is, in order to explain this, let's look at this thing. Let's suppose 100,000 years ago, there was some clay layer which was there, and then there was some flood which came maybe 20,000 years afterwards, and there was a new layer of soil, and then something else happened, and another layer of soil came on top, and further layers of soil came on top. You know, this is how the soil was formed. This is how our planet was formed. This is why when we dig a borehole, for example, today, somewhere we find sands, other places we find clay, and other places we find rock. This is what happened in the geological history. Okay, so you see, this, if I talk about this clay layer, since we are talking about consolidation, so obviously we are interested in the clay layer behavior only. So talking about this clay layer, if I ask you that the current overburden pressure on the soil, the current overburden pressure on this clay layer, was the clay layer ever induced to a higher pressure than the current pressure? So your answer would be no. This is the maximum pressure that has ever been imposed on the soil. Such a soil in which the current state of pressure of soil is the maximum pressure that the soil has ever experienced in its entire history is known as a normally consolidated soil. So for a normally consolidated soil, the present effective stress, so for this clay layer, the present effective stress or the overburden pressure is the maximum pressure that this clay layer has ever experienced in its past history. So such a soil is known as a normally consolidated soil. So for a normally consolidated soil, for a normally consolidated soil, so for a normally consolidated soil, the pre-consolidation pressure, this pre-consolidation pressure is almost equal to the present effective stress or the present effective stress. So it means that this is the pressure that is the maximum pressure that has been experienced ever by the soil. So this is, in this case, the soil is called as the normally consolidated soil. Now, the concept of normally consolidated soil might get a little more clear when we talk about the second type of consolidated of soil, which is called as the over-consolidated soil. Now, let's suppose the same clay layer as we have seen previously. So this same clay layer was there was there were different layers coming on top of it. But what happened was sometimes in its geological history, some change occurred, and it was subjected to ice age, and there was a huge glacier of ice which was present on top of it. Now you can imagine what has happened is that this clay layer is subjected to a large pressure. Now this was maybe 18,000 years ago, but then in the geological history, some changes occurred, some global warming probably occurred, and this ice got melted. This ice got melted, something else happened, and some new layers came on the soil, and a couple of more layers came, and we reached present state. Now, in this present state, if I ask you the same question that I had asked you in the previous slide, now what do you think? Is the current pressure on this clay layer, the current stress on this clay layer, is this the maximum stress that this clay layer has ever been subjected to? So obviously your answer would be no. In the past, there was a huge glacier of ice which was present. So obviously during that time, this clay layer was subjected to a greater pressure than today. Now, such a soil which was subjected to a higher load in its past compared to the present load is called as an over-consolidated soil. So the simple definition of an over-consolidated soil is the present effective stress is smaller than the effective stress experienced in the past. What it means is the present effective stress is smaller than the pre-consolidation pressure. What is the pre-consolidation pressure? Pre-consolidation pressure, we already defined, is the maximum pressure that has been experienced by the soil in its past history. So you see, the present overburden pressure is less than the past overburden pressure. So such a soil is called as over-consolidated soil. So you see, when we talk about the over-consolidated soil, so over-consolidated soil is lying somewhere over here on this line. But when we talk about a normally consolidated soil, for normally consolidated soil, we are probably lying somewhere here on this graph. So I hope it might be a little clear, this difference between the normally consolidated and the over-consolidated soil. So following these two definitions, there is a new definition that you should know of, and that is called as the over-consolidation ratio. Now, what is an over-consolidation ratio? The over-consolidation ratio is the ratio between the pre-consolidation pressure, which is the maximum pressure that has ever been sustained by the soil in its history, divided by the present effective overburden pressure. Now, going by this definition, what do you think would be the over-consolidation? What would be the over-consolidation ratio for normally consolidated soil and the over-consolidated soil? And then, in fact, there is a third type of soil which are called under-consolidated soils as well. So for normally consolidated soil, we already discussed this thing that for normally consolidated soil, the present overburden pressure is almost equal to the present overburden pressure is the same as the pre-consolidation pressure, meaning the present pressure on the soil is the maximum pressure that has ever been sustained by the soil. Means the pre-consolidation pressure is equal to the present effective pressure. If this is the case, if these two are equal, it means the over-consolidation ratio would be 1 for normally consolidated soils. However, for over-consolidated soils, what happens in case of over-consolidated soils, as we discussed in the previous slide, for over-consolidated soils, the past pressure was much larger compared to the present overburden pressure. This past pressure would be much larger than the present overburden pressure. So if the past pressure was larger, it means this over-consolidation ratio should be greater than 1 or should be less than 1. Yes, if the past pressure was larger than the present pressure, it means the over-consolidation ratio should be greater than 1. And then finally, there is a third type of soil which are called the under-consolidated soils, for which have an OCR value less than 1. And what are under-consolidated soils? I have just written a definition of under-consolidated soils for you. I'll briefly explain. Under-consolidated soils are the one which are actually undergoing the process of consolidation. It means these are the soils which have for which consolidation has not been completed and they are undergoing the process of consolidation. So such a soil is known as under-consolidated soil. And these are the soil which have an over-consolidation ratio less than 1. So you have seen that in case of clay soils, the stress history plays a significant role. The behavior of the soil totally changes whether whether the current state of stress is less than the pre-consolidation pressure or more than the pre-consolidation pressure. The behavior totally changes. If the behavior is in this zone, then for the determination of magnitude of consolidation settlement, we have to use recompression index. And if the behavior is in this zone, then for the determination of settlement, we have to use the compression index. So this thing tells us that this pre-consolidation pressure is a very important phenomena, is a very important parameter for any soil. So the question is how to determine this pre-consolidation pressure actually. Now this is obviously an idealized figure in which there is a very clear curvature between these two lines. So in this case, it is very easy for me to tell, okay, this is the point of maximum curvature. From this point of maximum curvature, I just draw a line and call this as my pre-consolidation pressure. But the question is, in actual, how do I determine this pre-consolidation pressure? Because this is just a schematic figure that I have drawn here, but the actual figure is not so clear and distinct. Rather, the actual figure looks something like this. The actual E versus log P graph looks something like this. Now, in this graph, there is no sharp turning point from where I can say, okay, this is my pre-consolidation pressure. If there is no sharp point, how can I then determine the pre-consolidation pressure? So again, there are a couple of ways by which we can determine the pre-consolidation pressure. The first method that we are going to use is called the Cassegrain's method. Now, how can we determine the pre-consolidation pressure by using the Cassegrain's method? So there are a number of steps that I'm going to try and explain here to you. So step number 1, by visual inspection on this curve, try to locate the point of maximum curvature. So what do you think is the point of maximum curvature? So let's suppose to me this point A appears to be the point of maximum curvature. So whatever I think is the point of maximum curvature, I just draw a point over there. Then at this point, I draw a horizontal line like this. Once I've drawn the horizontal line, then I draw a tangent to this point. So step number 1, I draw a point of maximum curvature. Step 2, from this point, draw a horizontal line. Step 3, draw a tangent to this line. And step number 4, is determine the angle between these two lines. Let's suppose this angle is theta. We need to divide this angle theta into two equal parts. So once we divide this into two equal parts, so after dividing it into two equal parts, what we need to do is we need to extend this line backwards. We need to extend this line backwards by using this green line, for example. Where these two green lines meet, this is the point which point B, which actually represents my point of pre-consolidation pressure. So this is what we call as the Casagrand's method for the determination of pre-consolidation pressure. So by following these steps, we can determine the pre-consolidation pressure. So the same steps that I have explained to you, the same steps I have summarized here for you as well. So this is the most commonly used method for the determination of pre-consolidation pressure. However, there is a simplified method to this as well. And since it is a simplified method, so obviously this simplified method is good for initial estimates, but it will not give us very accurate results. So what we can do is, according to the simplified method, we need to draw two tangents. First tangent, and we draw the second tangent, and then we simply locate the point of intersection of these two tangents. So this point of intersection is something we call as the pre-consolidation pressure. So again, the steps are very simple. We simply draw two tangents, and the point of intersection of those two tangents is what we call as the pre-consolidation pressure. So as I explained earlier, this procedure is although simple, but it's not very accurate. So it should only be used for preliminary estimates and not for final estimations. So that's pretty much it for this lecture. But before I finish, I just want to show you one more slide. In all this lecture, we have been talking about this E versus log P graph. But throughout this lecture, we have been looking at the schematic figures of the E log P graph. So all of these are schematic illustrations that I have shown you. Let me just show you a real E log P graph, which is based upon the real test data. So this graph of void ratio versus pressure, and you see this is not the normal scale, this is the log scale. So this is the graph, E log P graph for an actual consolidation test data. And as discussed earlier, in this graph, this first part shows the loading curve, and we increase the load, apply the first loading increment, and we determine the void ratio here. We apply the second loading increment, and the void ratio reduces. We apply the third loading increment, maintain this loading increment like the previous ones for 24 hours, and determine the void ratio. And in the same way, we apply different loading increments, each loading increment applied for 24 hours, and each loading increment double of the previous loading increments. So by doing so, we can plot the loading curve. Once we have applied the maximum load, then we start removing the load and reducing the applied pressure. And when we reduce the applied pressure, you see the void ratio keeps on increasing a little. So this is the unloading part. And we have also discussed that the slope of this loading part is called as compression index, and slope of this unloading part is something we call as the recompression index. Now, that's it for the day. I would want you to concentrate on this final graph of E versus log of P, because like the previous lecture, there would be another assignment for you. And in this assignment, you have to plot the E versus log P graph. So you have to think how to determine the pressure, how to determine the void ratio, how to do it all. So obviously, I'll be available for the discussions. So let's see how you take up with that assignment. So that's it for the day. Thank you very much.